Hello. In this third lecture on the PIC microcontroller 16F877, we are going to study some additional functional blocks in the device. This microcontroller has a special port called as parallel slave port. We'll discuss this port at the beginning. Then we'll discuss the timer section of this microcontroller. This microcontroller has in all 3 timers which have different features. We'll discuss them in details. Then at the end we'll discuss the interrupt structure of this microcontroller. This device has in all 14 different interrupting sources. We'll discuss this interrupt structure in details. So currently we are discussing the IO ports section. So we have seen that this microcontroller has in all 5 different ports, right? Port A, B, C, D and E. Last time we have seen discussed all the ports. Before we close this, let us discuss about particularly the PSP mode of operation of port D. We have seen that port D is an 8-bit port. Otherwise it is like any other port can be used for I/O of data, but this port D has an additional feature that it can be operated as a PSP, parallel slave port. Okay, so let us try to understand how exactly this works. Port D works as a parallel slave port. So for example, suppose this is your microcontroller F877, the PIC microcontroller. When you operate your port D as parallel slave port, it is possible that you can connect an external I/O device which can transfer the data or which can read the data from this port, which can read or write the data to this port. Okay, so this is your port D. It is RD0 to RD7, port D. When you are operating this as a PSP, parallel slave port, then it will be associated with 3 handshake signals which will be provided by the external device, and those 3 handshake signals are received over 3 bits of port E. Okay, so suppose this is RE0, RE1 and RE2. These 3 pins of port E, they receive the 3 signals which are typically chip select signal, read bar and write bar. So that's how the connections are to be made when you want to operate your port D as a PSP port. Port D as parallel slave port, PSP. That means whenever an input device sends the data, it can put the data here on this data bus which is connected to port D. Then it has to select the chip. It has to activate this particular signal, CS bar. It has to make it low, and then apply a write bar pulse so that the data will be written into this port. Or whenever this device wants to read the data from port D, again it has to select the chip by activating this signal and generate a read bar pulse. So, in this manner it can read or write data with this port. It can be another microcontroller also, you can understand. Any device which is capable of generating this kind of signals can be connected here. Okay, this is on one side of the communication. On the other side of the communication, see, whenever this, for example, suppose this sends the data to this port, then the CPU of this microcontroller has to read the data. It may save the data to some memory location, or it may be possible that the CPU of this particular microcontroller sends the data to this port, and that data is finally read by this external device. So, on the other side of this communication, there is a CPU of this microcontroller. How CPU knows that such data is available? Okay, so for that there are some handshake bits, and they are there in TRIS E register. Yesterday we have seen that some bits of TRIS E register, you can see here. So, this is a TRIS E register. Lowest 3 bits, they do their usual task, like the bits in a TRIS type of register. You know, they are used to decide whether the port E bits will be either input bits or output bits, because port E is only 3-bit port, only 3 bits of this register will be used for that purpose. So, that is the usual function of TRIS register, but remaining some bits, particularly upper 4 bits, they are used for this PSP mode of operation. Okay, now here you can see some handshake signals. These can be read by the CPU of this microcontroller. Actually, one of this bit, for example, this PSP mode bit is a writable bit. Particularly when you want to operate port D in PSP mode, this particular bit is to be set. So, this is set by your CPU, or through the program you can set this bit. So, as soon as you set the bit, then port D will go in PSP mode, and in that case these are the connections required. Okay, so that is why you can understand that this bit is writable bit, but all the remaining 3 bits are just readable bits. Okay, so these are handshake bits, and this can be read by the CPU to understand the current situation of the data flow. Okay, so for example, you can see that the bits are as usual input buffer full and output buffer full. So, whenever, for example, the external device sends a data to this port by generating write bar pulse, then that input buffer full bit will be set. Okay, it will tell the CPU that a data is available in this port. Okay, and then the CPU can read the data, and it can be saved in some memory location. Similarly, output buffer full is typically used when the data is being sent from the CPU to the external device. Okay, suppose the CPU is sending a series of bytes to the external device, then it will send 1 byte, second byte. Say when 1 byte is sent out, then OBF signal will become active. It will indicate that output buffer is full. Okay, when that particular data is read by the external device by generating read bar pulse, then this buffer becomes empty. So, OBF signal will become inactive. Okay, when it goes inactive, then the CPU can send the next byte, right. So, OBF signal is typically used by the CPU when the CPU is outputting some data to the external device. Okay, the OBF signal is used to verify whether the previously sent data to the port D has been read by the external device or not. Okay, so that is how the synchronization is achieved. Similarly, IVF signal is used when the CPU of this microcontroller is inputting data from the external device. As soon as the external device puts some data here by generating write bar pulse, the IVF signal becomes active. That IVF bit becomes active, and that tells the CPU that byte is available, it can read the byte. Okay, so that is how these 2 bits are used, IVF and OBF, as per their usual meaning. One more bit is provided, which is input buffer overflow. Input buffer overflow detect bit. Okay, so it means that this will indicate that there is an overflow, or a byte has been written into the buffer before the previously sent byte has been read out. Particularly while inputting the data, if the external device sends the data here, and suppose the CPU is engaged in doing some work, then it may be possible that CPU may not read that byte immediately. But during that interval, suppose the external device sends another byte, then that byte will get overwritten. Okay, so as soon as this situation occurs, then that overflow bit will set. Right, that will tell the CPU that there was an overflow. So there is some missing bytes. Some bytes have been missed. Okay, so that type of error indication is done by this particular bit. Okay, so that's how these bits are handshake bits, particularly 3 bits, which are used as handshake signals by the CPU while reading or writing the data with the external device. And PSP mode bit is actually used to set the port D in PSP mode of operation. Okay, if this bit is 0, then port D will work as usual IO port. Okay, in that case, these signals will have no relevance. These will be don't care bits. Is it clear? Okay. So that was about the PSP mode of operation of port D. So we have discussed the IO port section of your microcontroller. We have discussed the features of all the ports. Okay, I think we can go next now to discuss the timer section in short. Okay, because timer section is needed for study of higher other functional blocks that we are going to discuss after this. So let us begin with the timer section. So your microcontroller 16C, this microcontroller 16F877 has in all 3 timers. Okay, so if you consider this IC 16F877, the device which lies at the highest end in the family PIC family, then this highest device has 3 timers. Okay, timer 0, 1 and 2. If you remember, we have discussed 16C61 device, which was at the lowest level in the family of PIC microcontroller family. This microcontroller had only timer 0, only one timer. So this was available in the lowest device also. Okay, so these 2 were not available here. These are now newly added. Okay, such 3 timers are there. We will discuss all these timers one by one. Okay, timer 0 is actually same as it was there in your lower device, which we have already discussed. The timer 0 we have discussed in details while studying this microcontroller last semester. It is same as that. You understand that every higher family member in this microcontroller family is made LoR compatible. That means whatever infrastructure is available in all the lower devices, the whole infrastructure is available in all the higher devices as it is, with some additional facilities. And therefore, when you have this timer in lowest device, it is definitely available in this highest device. You know, timer 0 is an 8-bit timer. You know that it's an 8-bit timer. It's an up counter. You know, the count goes on increasing from 00 to FF, and when it overflows from FF back to 00, the counter matures, and then the corresponding timer flag is set and the interrupt is generated. Okay, so this we have seen. So actually this is an 8-bit timer counter with prescaler. It is with prescaler. This we have discussed last semester. So if you consider the timer, you can see it here. So that's the block diagram of timer 0. Because it's basically a timer, the clock is taken from the CPU oscillator. It is internally divided by 4, because you know, in case of PIC microcontroller, every machine cycle is made up of 4 clock cycles, and therefore the count increments after every after every machine cycle. That means after every 4 clock cycles. So effectively the frequency is divided by 4. Then there is a prescaler. Okay, and then that count will be incremented. 2 cycle delay simply indicates that when you change the prescaler, the action will take place after a delay of 2 cycles. That's all. Okay, whatever prescaler is there, that will divide this frequency further, and depending upon that frequency, this count will go on incrementing. Right? When this count, which can be as small as 00, 8-bit count, when it goes on incrementing, and when it overflows above FF back to 00, the corresponding timer 0 interrupt flag is set. Okay, that flag is available in the interrupt control register. Okay, one more bit is there, which is timer 0 interrupt enable bit. Okay, so when that bit is set, then the interrupt is enabled and that interrupt is generated. Okay, if you know that if the timer interrupt is disabled, if this bit is reset, then when the timer matures, only flag will set. But because this is 0, this interrupt will not be generated. Okay, one more thing which is required here is that the global interrupt enable bit should be set. You know this global interrupt enable bit. When you reset this, all the interrupts are disabled. So whenever you want to use any interrupt, this bit should be set, and the enable bit corresponding to that interrupt should also be set. Okay, then that interrupt will be generated. Okay, so this is the operation that you have already studied last year. So that is about your timer 0. The control bits for timer 0 are available in the option register. Control bits are available in the option register. Just now we have seen that a prescaler. Okay, the prescaler for this timer is provided by these 3 bits, PS2, PS1, PS0, you know that. Right? This is prescaler assignment bit. So that when that bit is made 0 particularly, then this prescaling will be assigned to timer 0. Okay, so that's how you can divide the frequency minimum by factor 2, maximum by a factor 256. Okay, so you try to understand that because of this prescaler, effectively your timer becomes a 16-bit timer. Time. Okay, so when when it is FF, the frequency will be effectively divided by 256. And when it is divided by 256, effectively it becomes a 16-bit timer, because 8-bit timer is already there. Okay, so that's how this frequency can be divided, and further it will be divided by this 8-bit count, which is there in the timer count register. There are timer 0 clock selection bit. Okay, this bit decides whether your timer will work as a timer or it will work as a counter. When it is working as a timer, the clock signal is taken from the CPU clock, as we have seen in the previous diagram, FCPU upon 4. But when you set this bit, then the input clock will be taken from one pin, which is timer 0 clock input pin, which is alternate function of port A pin, RA4. Okay, so whatever signal you supply there, clock signal, that will be taken as the input clock. Okay, so in other words, when this is high, your timer 0 will work as counter.
that means in short, this particular bit decides whether it will work as a counter or timer. Okay, then this particular bit, timer 0, source age select bit. Particularly when you are operating this as a counter, you will be applying some clock signal through this pin. Okay, so this bit will decide whether your count will increment when the clock signal makes high to low transition or low to high transition at the falling edge or rising edge. Okay, so you can make the counter either falling edge sensitive or rising edge sensitive based on this particular bit. So it means that all these control bits for this timer 0 are available in the option register. Right? Remaining 2 bits are used for some other purpose, as you know. Okay, so there is no separate control register for timer 0. Clear? So we have seen that a timer 0 is same as before, as we have discussed before. So now let's go to the next timer, which is timer 1. Timer 1. Timer 1 is actually a 16-bit timer counter. It's a 16-bit timer counter. It can work either as timer or counter. It's a 16-bit. It's a up counter, as usual, up counter. So when it overflows from FF to 0000, then the corresponding flag will set. This has a prescaler. Okay, which prescaler? Okay, so the only difference between these two is that it is a 16-bit timer counter. Okay, the typical structure of this can be shown like here. This is your timer 1 structure. This is your timer 1. You can see that it has a 16-bit count register where you can store the 16-bit count initially, and that count will go on incrementing with every input clock pulse. There is a prescaler. We will see that how to set that. But that prescaler can divide the input frequency by minimum factor of 1 up to 8. Okay, then this is it can work either as a counter or a timer. In the timer mode of operation, the input signal will be taken from CPU clock. In the counter mode of operation, it will be taken from outside through this particular pin of this microcontroller. Particularly the port C pin, RC0, has alternate function of timer 1 clock input. Okay, so whatever signal you supply here, that signal will be taken as clock and it will work as a counter. As soon as this particular count overflows from FF to 0000, the corresponding timer flag will set and the CPU will be interrupted provided the corresponding interrupt is enabled. Okay, we will see that this particular interrupt flag is available in a register called as peripheral interrupt register. For timer 0, we have seen that the interrupt flag was available in your option register, but here it is available in some separate register, peripheral interrupt register 1. Okay. Then this prescaler, deciding of the prescaler and deciding whether it will work as a timer or counter, is done by using these bits. These bits are in the timer 1 control register, T1 con register. Okay, let us see that register, timer 1 control register. This is timer 1 control register. A separate control register is provided for controlling the timer 1 operation. Here there are two bits, timer 1 clock prescaler 1 and timer 1 clock prescaler 0. These two bits, they decide the prescale. Either the input frequency is passed as it is, or it can be at the most divided by factor 8. Then there is timer 1 clock select bit. You can see here that this clock select bit will actually, timer 1 clock select bit will decide whether the timer will use internal clock or external clock. Internal clock means it will work in the timer mode, and external clock means it will work in the counter mode. Okay. Now there is timer 1 SINAC bit. This bit is typically used when this bit is 1. This particular bit is 1. 1 means you are operating in the counter mode. When you are operating your this section in counter mode, you are actually receiving the clock pulses from outside, right? External. Okay, so what we are doing is that in this case, so just now we have seen that when you are operating in the counter mode, the clock signal is taken externally through RC0P. So this is RC0P. Basically, it has alternate function of timer 1 clock input. Okay, so here you may supply some clock. Okay, so suppose at rising edge, suppose you select the rising edge, at the rising edge of this clock, the count will get incremented. Okay, now there is a bit just now we are observing, the bit is timer 1 SINAC bit. See, this bit when it is 1 means do not synchronize the external clock with the input, and if this is 0, timer 1 clock is 0, then it means that synchronize. When it is 1, then do not synchronize, but when it is 0, it means synchronize the external clock input with the internal clock. Okay, so this is an active low bit, you understand. It is timer 1 SINAC bar, actually it should be bar here. So it is active when it is 0. Okay, so when you make it 0, what will happen is that whatever external clock you apply, that will get synchronized with the internal clock, and then the actual action will be taken. Okay, so for example, suppose this is the clock pulse you are supplying externally. Then normally what may happen is that at this instant itself, the count will increment. The count will increment, n will go from n to n plus 1. Okay, that will happen when that SINAC bar bit is 1, inactive. Okay, but when you make SINAC bit active, that means you make it 0, then actually this will get synchronized with the clock. So that means suppose this is your input clock pulse, then even though this edge occurs here at this instant, exactly at the same instant the action will not take place, but this will get synchronized with the CPU clock. there is some CPU clock having some higher frequency. Okay, so what will happen when this edge has occurred? The actual action will be taken at the next rising edge. Okay, so just forget about this. So if the clock is like this, then even though the edge has occurred here, the action will not be taken immediately, but it will be taken at the next rising edge of the clock. So action will be taken here. Okay, so the count will actually increment n to n plus 1 at this instant of time and not at this instant. So that is what we mean by synchronizing the external clock pulses with the internal clock. Okay, so that is what is meant by that is the use of this SINAC bit. Okay, if this SINAC bit is 1, it is inactive, then this is ignored. Okay, as soon as this edge occurs, it will be immediately incremented by 1. Okay, so count will be incremented asynchronously. Is it clear? Hello? Hello? Is it clear? Okay. Okay, so that's how this bit works. Then there is timer 1 on bit. Okay, so this bit switches the timer 1 section on or off. Okay, so when this bit is 1, okay, you can see when this bit is 1, it enables the timer. When it is 0, it stops the timer. Actually, what happens if you don't want to use the timer for any for a given application, then you can keep this bit 0. So timer section will remain off. That means it will not consume the power, right? In any application, one of the applications, suppose in a given application, you are not you don't need timer 1, then you can keep it off. So that is how, that means when you want to use this timer, first of all it should be switched on by making this bit 1. Okay, now there is one more bit which is timer 1 oscillator enable. Okay, you can construct an independent oscillator by using timer 1. It's an additional facility available with timer 1. Okay, by connecting an external crystal to timer 1 directly, it is possible to construct a separate independent oscillator, and this bit will enable or disable that oscillator operation. Okay, so that means for normal use of the timer, this bit may not be needed, but when you want to use the timer 1 as oscillator, independent oscillator, this bit can be used, set or reset, to enable or disable the timer 1 oscillator. Oscillator enabled, oscillator off. Okay, so these are the different control bits in this. Okay, so you can see that the 2 bits are provided here. These 2 bits. Here you can connect a crystal externally. Oscillator 0. So this is for timer 1. Timer 1 oscillator. You can see. Timer 1 oscillator 0, timer 1 oscillator 1. So it is possible that you can connect a crystal here, and that can be used by the timer 1 to generate independent clock signal. So that is use of timer 1 as an independent oscillator. The usual oscillator of this microcontroller, which is the CPU oscillator, that is operated by using this crystal, the crystal which is connected here. Oscillator 1, oscillator 2, pin number 13, 14. That is for the CPU oscillator, which is for the basic functions of all this microcontroller. but this is an additional oscillator which you can construct by using this oscillator. So that's how you can see this timer 1 control register. We have seen this. Is it clear? Okay. So now let's go to the next one, which is timer 2. So next timer is timer 2. Timer 2 is an 8-bit timer. 8-bit timer. It is timer only. It cannot be operated as counter. It is timer only. With a pre-scaler and post-scaler. So frequency can be divided at the input of the timer as well as at the output of the timer. Two different scalars are available. And this timer typically has auto reload facility. Auto reload facility. Okay. Both these timers were not having auto reload facility. That means when the timer matures, it will restart from FFFF. Restart from 0000 always, until you load the count manually. Initial count will not be automatically reloaded. Okay, but here that auto reload facility is provided, and this has pre and post scalars. Okay, the control register for this is obviously timer 2 control register, T2 con register. Let us see that register first. Okay, before that you can see first this one. Okay, so this is your, okay, both the things are shown here. This slide shows the details about timer 2. You can see this block diagram of timer 2. Just now we have seen that timer 2 is an 8-bit register. Sorry, it is an 8-bit timer. So this is the count register. TMR2 is the 8-bit count register. Then it has a pre-scaler as well as post-scaler. Pre-scaler can divide the input frequency. This is only timer, you can understand. There is no signal which is coming from outside. Clock signal will be always taken from the your CPU clock. Okay, the pre-scaler can divide the frequency at the most by 16. Post-scaler can also divide the frequency at the most by 16. Pre-scaling and post-scaling is decided by the corresponding bits in this control register. Timer 2 pre-scaler 1 to 0, timer 2 pre-scaler 1 and timer 2 pre-scaler 0, right? These two bits these two bits will decide the pre-scaling. So these two bits will decide the pre-scaling. So these are pre-scaler bits. This one, and you can see that their combination 0001 and 1 don't care. So frequency will be divided either by 1, 4 or 16 at the most. Here pre-scale. Then that clock will be used actually as the input clock to this timer section. Then output of this timer is again divided by a post-scaler. There are 4 post-scaler bits, 4 post-scaler bits. Timeout, timer output, scalar bits, post-scalar bits. So this is 3, 2, 1 and 0. So this is post-scaling. And that combination is shown here.
You can divide the frequency either by 2 or 3 up to 16. There are 16 combinations. So that's how this frequency is divided by these bits. And that finally that output finally goes to the timer 1, timer 2 flag. Right. So then the flag will set. When this matures, the flag will set, and this thing interrupt will be generated if the interrupt is enabled. Okay, so that's how your timer basically works like this: pre-scaling and post-scaling. So you can understand that because your timer is basically an 8-bit timer. Suppose pre-scaling and post-scaling was not available, then this timer will divide the frequency at the most by 256. Divide the frequency at the most by 256. Right? 8-bit timer. Because there is a 16 divided by 16 pre-scaler and divided by 16 post-scaler, the frequency will be additionally divided by 16, 16, and additionally divided by 16. Okay, therefore effectively the frequency can be divided at the most by 256 into 16 into 16. That is, it can be divided at the most by 64 kilo. If you calculate this, it comes out to be 65,000 something, so 64 kilo. And when you say that it is divided by 64 kilo, it means that effectively it's a 16-bit timer. It is a 16-bit timer, effectively. Because if you have a 16-bit count register, then the frequency will be divided by 2 raised to 16. That is 64 kilo. Right? Here the count register is only 8-bit. But because of additional availability of pre-scaler and post-scaler, effectively this timer can be at the most used as a 16-bit timer. Okay, that is one thing. Secondly, you can see that this particular timer has auto reload facility. So for that there is a comparator, and there is another register called as period register. This is period register. Period register. That means while using this timer, first of all you have to load some count here. Suppose you load count say AA here, and then you start your timer from 00. You load this by 00, and then you start a timer. So with every clock pulse, this will go on incrementing by 1. Comparator will keep on comparing this with this count. Okay, and when this becomes equal to this, after a certain number of pulses, when this becomes equal to this, then this will be automatically reset back to 00. Okay, and therefore your counting will always go from 00 to AA. At AA it will mature, so again it will go back to 00 to AA. So you understand this. So this is a sort of auto reload facility. The initial count is automatically reloaded, or in other words, here it's a up counter, so your counting will go up to that initial count or up to the certain count. In all the previous timer operations, timer 0 or timer 1, the counting will go from 00 to FF. You cannot abort it in between. Only after FF it will go back to 00. But here it can be aborted at certain count, and that count you have to put in period register. Okay, and therefore this is a sort of having auto reload facility. Is it clear? Okay.
So here once again you can see that there is a timer 2 on bit. Same function as timer 1 on bit. If you don't want to use this timer in your application, you can keep it off. Okay, if you make this bit 0, then this section will remain off, so it will not consume the power. Care has been taken because see, in a given IC, in a single IC, many facilities are provided. 3 timers, number of facilities are provided. But in a given application, all the facilities may not be needed. If you don't need a facility, then it is better to keep it switched off. Okay, otherwise that circuit will keep on consuming the power, because many a times automatically controlled systems may be battery operated, and whenever the system is battery operated, you have to worry about the power consumption. ज्या गोष्टी तुम्ही वापरत नाही आहात IC मधल्या, त्या जर स्विच ऑफ करून ठेवण्याची सोय असेल तर इट इज बेटर. Okay, so you can see that kind of facility here, that you can keep this timer off if you don't want to use it. Okay, once we have done this, then I think we have discussed all the 3 kinds of timers. Actually, okay, so these timers will be needed while discussing the further sections, functional blocks. Okay, let's go ahead. Okay, now let's have a look at it. This is about your interrupt. Interrupt structure of this microcontroller. You can see some registers: interrupt control register, PIE, peripheral interrupt enable register 1, peripheral interrupt register 2, peripheral register 1, peripheral register 2. Okay, so these are some registers here. So let's try to understand the interrupt structure, because every functional block that we are going to discuss, that we are discussing, is associated with its own interrupt, right? Actually, in this microcontroller there are in all 14 interrupting sources. 14 interrupting sources. So now what we are talking about in short is about interrupts. Right. Interrupts in this microcontroller, there are 14 interrupting sources. Out of that, 3 are basic interrupts, called as basic interrupts. That means the interrupts which are available even in the lowest device. And those basic interrupts are, external interrupt, RB 0 oblique interrupt. There is an interrupt pin to receive the external interrupt. So only single external interrupt pin is there. Then it is port B change interrupt. Port B change interrupt. Whenever any one of the bit of port B changes the status, the port B change interrupt is generated. And there is timer 0 overflow interrupt. timer 0 interrupt. Okay, so these can be called as three basic interrupts. These are also available in the basic device, which is 16061. Okay, so this is one group of interrupts. Second group of interrupts is called as peripheral interrupts. Peripheral interrupts. Peripheral interrupts. All the remaining, that means 11 interrupts, are taken together as peripheral interrupts. So every section, functional block, has its own interrupt. Just now we have discussed that timer 1 has interrupt. Timer 1 has its interrupt. We have seen timer 2 has its own interrupt. There is an A to D converter. We will discuss that later. So A to D converter has its own interrupt. Okay. There is a PSP, parallel slave port, port D. It has its own interrupt. Okay, so in this manner you may count a number of interrupts which are available, and that comes out to be total 11. Serial interrupt, capture, compare and PWM modules interrupts, 1, 2, etc. So there are 11 such interrupts associated with 11 functional blocks. All these interrupts together, they are called as peripheral interrupts. Okay, every interrupt has two bits. One is interrupt enable bit. Every interrupt has two bits. Interrupt enable bit to enable or disable the interrupt, and interrupt flag bit. Interrupt flag bit. So when particular interrupt occurs, the flag is set, and depending upon whether it is enabled or disabled, the CPU will be interrupted or not interrupted. Okay, so the bits corresponding to these basic interrupts, they all are available in register called as interrupt control register. Interrupt control register 0. Sorry, it's not 0, interrupt control register. Okay, so all the corresponding interrupt bits are available in this control register. And these bits corresponding to peripheral interrupts are available in different registers which are called as peripheral interrupt enabled 1, peripheral interrupt enabled 2, and peripheral interrupt register 1, peripheral interrupt register 2. Okay, so these two registers, they contain enable bits, and these two registers, they contain flag bits. Clear? So all the bits associated with this are available in interrupt control register. Okay, for example, your interrupt control register will contain the bits like INT E, INT E, and external interrupt enable bit, port B change interrupt enable bit, timer 0 interrupt enable bit. So these are enable bits of these three, and corresponding flag bits, external interrupt flag bit, port B change interrupt flag bit, and timer 0 interrupt flag bit. So these are flag bits. Okay, so these 6 bits are available here. In addition to that, there are 2 bits which are available, which is global interrupt enable, to enable or disable all the interrupts at once, and peripheral interrupt enable, peripheral interrupt enable bit. Okay, when you reset this bit, global interrupt enable bit, then all the interrupts are disabled. But if you set this bit and you reset this bit, then only peripheral interrupts will be disabled. That means when you reset this bit, only these interrupts will be disabled. Right? These bits will remain enabled. These interrupts will remain enabled. Okay, so such 2 bits and these 6 bits, so total 8 bits are available in this interrupt control register. Okay, and as I told you that the corresponding enable and flag bits for these 11 peripheral interrupts, they are separately available in these 4 registers. Okay, so once you understand this, then you can have a look at this interrupt registers. Just now I explained you interrupt control register, right? You can see here. Okay, interrupt enable register. Global interrupt enable bit, peripheral interrupt enable bit, then 3 enable bits for basic interrupts, 3 flag bits for basic interrupts. Okay, then you go to PIE, peripheral interrupt enable register 1. So these are all enable bits for different interrupts. So these are 8 interrupts. PIE2 register, these are 3 bits. So those 8 plus these 3, so 11 enable bits for the 11 peripheral interrupts. Similarly, PR1 register, so these are flag bits for 8 peripheral interrupts. And when you go next, these are 3 flag bits, so 8 plus 3, 11. So total 11 flag bits for the peripheral interrupts. Okay, so PIR2 and PIR1, they hold 11 flag bits, and PIE2 and PIE1, they hold 11 enable bits, which are for peripheral interrupts. Okay, and this is for the basic 3 interrupts. Such 14 interrupting sources are available in our microcontroller. As we are going to discuss the different sections like CCP sections, and after this, in the next chapter, we will be using these bits, enable bits, flag bits, for our programming. That's why I just told you how these are located in which registers. Is it clear? Okay. I think we can stop today. Next time we'll begin with I think one chapter we have finished. Chapter 10 is over from your everyday book. We'll now go for chapter 11 next time.